Welcome to our N3AS seminar. Today we are very pleased to have Jay Wadekar from IIS Princeton, and he will be talking about gravitational wave searches. Over to you, Jay.
Okay. Hey, thanks a lot for the invitation to talk at this network. I am Jay Wadekar. I'm a postdoc at the IIS in Princeton, and today I'll talk about some results from a new search that we have done, where we have included harmonics beyond the quadrupole harmonic in gravitational waves. So this has been work done with few people mentioned here who are at UC Santa Barbara, Caltech, and in Weizmann. Just to mention earlier, none of us are in LIGO, but we have used the public LIGO Virgo data to perform the search using a pipeline, which I think Liang was also a part of, like making some significant improvements in the beginning. So let me just go ahead with some introduction. I guess everybody knows that till now LIGO Virgo and other people have found a lot of like binary black hole mergers, BNS mergers in the data. So right now the count is nearly 100. We have found nearly 100 total, nearly 100 BBH mergers in the data. And now we are also now able to study their populations and ask questions such that where do these black holes originate from. And then just to mention, there are already next generation of gravitational wave detectors planned. So currently in this plot, like there are these three populations which are being shown: neutron star, neutron star, neutron star, black holes, black hole, black holes. Currently we are like slightly worse than this A+ sensitivity, but then in the future there will be these better detectors like Einstein telescope and cosmic explorer, which using which we may be able to see every say black hole merger in the observable volume. So I thought of like maybe everyone in the audience is not familiar with like typical search methodology for gravitational waves. So I thought of like making a quick outline. Please feel free to ask any questions you have. So the first step in a search pipeline is that we construct a template bank. So this is where we choose some parameters in this range. So like for example, like this point, and then you simulate a gravitational wave waveform corresponding to this point and store it in a bank. So every dot in this parameter space, for example, corresponds to a gravitational wave waveform in the template bank. And what you do is when you have the real gravitational wave data, you convolve these templates with the data and try to see which one of them like matches the best and what is the signal to noise ratio that you get. So in the first step, when we convolve all these templates with the data, this first step gives you like nearly 10 to the 5 triggers. So just to get an idea of what the numbers are in the pipeline. So that's the first step. You convolve each detector time series separately. And the next step is then you rank these triggers based on the coherence in multiple detectors. For example, like I think this is 150914, or sorry, not 150914, one of the later events where you can see that multiple detectors are firing at the same time. So that increases the chance of this trigger being real as opposed to just some noise. And after this step, you can then have this layer of filtration where you pass the 100 best significant triggers to the final step of the pipeline. So the final step is you make a list with the 100 triggers, and then for each of these triggers, you do a full Monte Carlo run where you try to estimate like all the parameters of the binary, for example, their masses, or the spins, the redshift of the binary. So this is a very expensive step. So that's why like we have to like boil the data down into these nearly like 100 triggers to get to this final step. And so then one caveat on which this talk is based on is that currently in the searches, in the templated searches that have been performed by LIGO Virgo and other groups, only the 2-2 mode or the quadrupole mode of the gravitational waves that has been used in making these templates. And another assumption is that they have also only assumed that the spins of the black holes are aligned with the orbital angular momentum. And so we will try to go beyond this assumption in my talk. So first of all, let me just give an overview. The quadrupole mode is like the dominant mode in gravitational waves. So it's so these are like when I say quadrupole and higher modes, these are like spherical harmonics. You can think of them as like spherical harmonics. The quadrupole mode has frequency which is twice the orbital frequency. So for example, when you have like once the binary is in orbit, you get 2 cycles of the gravitational wave. So here is I've shown like a typical gravitational wave waveform, and so there other than this 2-2 mode, general relativity predicts that there should also be these higher harmonics. For example, like this 3-3 mode where the frequency is thrice the orbital frequency, and here I've shown also the sum of these 2 waveforms. So just to get you an idea, these higher modes they become important. So they scale as velocity to the power 1/3. So they become important when you are like close to the merger where your binary velocity is very high. Okay, so at this point we already know from GR that these higher harmonics should exist. So why have not we been including them in our template banks already? So one big reason is that the template bank size increases by a factor of nearly 100 as compared to using only like the quadrupole waveform. And the reason for this factor of 100 is because now we need to sample over like the amplitude and the phase of the binary. So you can think of it like, for example, I have the 2-2 mode and the 3-3 mode here. I have a degree of freedom in the 3-3 mode where I can scale the amplitude up and down. And then when I combine them, so these amplitude parameter as I scale up and down and I combine them, these will make like different templates. So the sum would look different. So those would be like different templates in the template bank. You can also change the phase where I can just shift this slightly left and right, and that will be the combination will look a bit different, and those will be also be like new templates in your template bank. And so just to give a visual a picture here, so here is like a mock template bank where you if you only include the quadrupole waveform, you have the crosses, and once you start including these higher mode waveforms, you can see that the number of points are much larger to cover this space. So the size increases nearly factor of 100. So this I think is one of the biggest problems when you search with for searching with these higher modes. And so we tried to I'll mention in a second the approach that we did to try to reduce this computational burden. But in terms of just some physical motivation for higher modes, so the importance of higher modes. So these higher modes, they are like, you can think of them as they are around like the amplitude is around 10% of the amplitude of the quadrupole. So these are not like the same order as the quadrupole, they are of a higher order. But even though they are like 10%, they are important because they can break important parameter degeneracies. So one I've shown visually like this. So if you have a binary, you can observe it to a larger to a farther distance in the face-on mode. But the binary waveform would look the same if it is an edge-on at a closer distance. So if you see some waveform in your data, you can not say whether it was this configuration or this configuration, just to give you an idea. So this is the famous degeneracy between distance of the binary and inclination. And as you all know, gravitational waves have been proposed as one of the candidates for determining H0. And so we need to know these distances very precisely because we know we would those are the ones that is the crucial parameter going into the determination of H0. And so these higher modes, they have a different dependence on the inclination. Like for example, the 3-3 versus the ratio has a different inclination, and this actually breaks this degeneracy. So you can measure distances to these binaries better if you include higher modes. Other important features, as I mentioned already, you can see in this formula, the amplitude depends on the velocity, and the velocity is closer like the higher the velocity, the more important these higher modes, and at these high velocities you are close to the merger and you are testing GR in the strong field regime. So I mean, that's one physical motivation for why you could think about higher modes. And also you can probe the properties of remnant better. Okay, so let me come back to this point of the computational burden that I talked about earlier. So what like previous searches have used is that so when they make the template banks, they do a combination of this dominant quadrupole mode and some higher modes. So for example, when you sample over the amplitudes and the phases of these modes, you can get different waveforms, and this is like all combined in their template bank. So their template bank includes all these combinations of these waveforms, and then what they do is they convolve the LIGO Virgo data with these templates and get SNR time series. So this is just like time on the x-axis and the signal to noise on the y-axis. So this was the approach that these previous studies had taken, but so we take a different approach. So what we do is we don't construct templates based on combinations of these different modes, but we convolve these modes with the data separately. So you would have a separate time series for the 2-2 mode, a separate time series for 3-3, and like for example the 4-4 mode, and you can combine them in a post-processing way after you collect this time series. And this helps a lot. So the computationally expensive step is when you match filter these templates with the data. And so that step is now only like 3 times more expensive than using the 2-2 mode. But in these previous searches, this step was like 100x more expensive. So now the cost of these higher mode search is just 3 times. So this is the approach that we use for the higher modes. There was another important improvement that we made in the pipeline, which is to improve sensitivity in the high mass regime of all the modes. So again, just to give everybody an idea of maybe people are not familiar, in gravitational wave data, you see a lot of noise transients, which people call glitches. For example, on the right, I've shown some of the popular like noise transients that are seen in the data. People have given all kinds of creative names. So this is called the koi fish, as it looks like maybe one. And so these glitches, I mean, they are like kind of blips in the data. And if you have low mass waveforms where you expect a nice chirp in the data, these don't damage those waveforms a lot. But then when you have like very high mass binary black holes, for example, like the mass of these black holes are like 280, 70 solar mass, then these real waveforms also start looking like some blips. And so then it becomes like hard to distinguish these from glitches. And so that's been like one area of a lot of work in the past. And so we try to develop some tools to reduce these blips or these glitches. So there are like one of the categories of these glitches is like these slowly varying glitches over a long period of time. For example, in the data above, you have these lines that are like seen in spectrograms. So so for people who don't maybe are not familiar, spectrograms are just time on the x-axis and the frequency on the y-axis. And so this was the data that if you trigger it with some pipeline, it has like 100 frequency mode, and it will trigger with like some binary black hole waveforms which have a lot of power near 100 hertz, for example. And so then we try to develop some tools like this band eraser where we could clean these streaks. And so it's just not just these streaks, but also these kind of blip-like things. We also try to, I mean, we use this tool which was also could clean some of these blip-like things going. So for example, like this is all like just spurious noise, as you can see in the figure, and we try to clean it. We developed this tool called band eraser. So I won't go into detail, but feel free to ask me more after the talk. Okay, another important improvement that we did in the case of these glitches is that we saw that these glitches they prefer some of the templates in the template bank and not some other templates in the template bank. So this is a plot like showing one example where you have say the number of triggers where some template fired as a on the x-axis is the signal to noise square. So if the data is completely Gaussian, it doesn't have these non-Gaussian transients. You expect the data to have a Gaussian distribution. For example, like as you increase in SNR square, the probability should go down as exponential. And so for example, like in a bank, you have multiple templates, and we realize that there are some templates which are quite clean. Like when you run them, you get noise as you would expect. But then there are some templates which are like we call glitchy, which are you can see that the number of triggers are like much. I mean, it doesn't like go down with SNR. So, for example, like if you have an event with SNR square 100, for example, and that event occurs in the clean template, you can say that that event is quite more significant than if it happens in a glitchy template. So this increases the sensitivity of our pipeline to some of these events. So in the last iteration, I think people were combining both of these templates into one group. But then you can see that they have different noise properties, and so we distinguish them in terms of their noise properties now, and take this into account in our analysis. Okay, so let me then jump to the new results that we found. So we did this. We included these higher modes. As I mentioned earlier in the search, and also then improved some sensitivity to high mass. So we are like currently working on the paper, but here are like the detections that we found. So in this plot, first of all, like the gray things, they are the events that have been detected earlier by the LIGO-Virgo collaboration. And also they include the events which have been reported by also other pipelines, for example, like the NITS et al. Or even the previous IAS pipeline iterations. And in the color, we have shown the new events that we have found in our search. So here I've shown just some properties of these new events on this in this mass M1 versus Z space. So M1 is the more massive component of the binary. And so you can see that, I mean, because of including these higher modes and due to this improved mass sensitivity to high masses, we have found like some new events which have not been reported in the literature earlier. And also let me mention this P astro is a parameter which people use to like define what you can claim as an event. So all the pipelines follow a standard bar that if the P astro in the pipeline is greater than 0.5, which means to say that these events can not occur due to noise alone within a run with some probability. So is just like a bar that every pipeline uses. P astro greater than 0.5 to claim a detection, and we use the same bar. And so there were these things we found which were higher than 0.5. And another thing to mention is we also found a lot of the significant detections that have been claimed earlier. So those were also found by our pipeline, but I've not colored them as I've not like put them in the plot as colors because they were already found earlier. And this plot, we wanted to highlight the new ones that we found. Okay, so apart from this M1Z space, okay, one important thing in this mass versus Z space, I guess people here are like experts in these things about can we like try to infer where these black holes originated from. So there has been on the detection side, there has been some interest of like trying to find events which are more massive than nearly like 50 solar mass, because then I mean in some of these like population channels for producing these black holes, there is a claimed mass gap which can occur, which is like shown in this diagram here. If you have mass below 50, you can have the remnant which forms a black hole. But if you have mass between like say 50 and 130, you can actually like have a pair instability supernova and leave no remnant behind. And to explain the physics, it would require some more time, but there are just like kind of like three areas in this channel. Below 50, you get a remnant. Above 150, you get a remnant, but in between, you don't get a remnant because you can have these pair instability supernova going off. And so this has been an interesting thing to probe in data. And so it is interesting that we have found like some of these new events in this regime. We are like further following up with a population study of these events. And another portion of the parameter space which is typically interesting is the total mass of the binary as compared to the chi effective. So the chi effective is a parameter to represent the spins of the black holes. For example, like chi effective is just the mass weighted spins. And so we in this catalog we have been seeing among the new detections, and also in the previous ones there has been like a slight like preference towards like positive chi effective. And so that has been interesting because chi effective has been one of the parameters which could maybe distinguish some of these channels that people have proposed to make these binary black holes. For example, in isolated channels, you can have you tend to have more black holes which are aligned with the orbital angular momentum. But in a dynamical scenario at the centers of clusters, you don't expect these black holes to align with the orbital angular momentum. So maybe like some of these new detections, once we do a population analysis, can maybe give interesting results about these channels. Okay, so let me see. Okay, so then after we had these detections, we tried to see whether some of them show preference for like higher modes and precession. And so these are like the new events that we found. These were like around 10, in total 13 right now. And you can see that some of these do have Bayesian evidence for there to exist higher modes apart from the quadrupole mode in their waveforms. And some of them also have evidence for higher modes and precession. But sorry.
There is a question by Anna. So sorry to interrupt you. There is a question in the chat. Anna, please unmute yourself.
Hi, Jay. Thanks. This is George Fuller at UCSD. Got a bunch of us at UCSD watching your talk. So on that previous slide, if I look at the data you had for the big ones, so it looks like statistically it could be that there's no correlation of alignment of spins. Is that right for the really massive ones? But the statistics aren't great at this point. Is that a fair assessment?
Sorry, can you repeat that? I didn't.
Yeah. I mean, so for the really massive guys that you find with the new analysis, it looks like there's kind of weak evidence that the spins are not correlated.
You mean like the chi effective is like not zero? You mean?
Well, I'm thinking it's closer to zero. It could be closer to zero. If I look at that. Yeah, that one.
Yes. For some of them, yes. Yeah, but like some of them, so these are like 50% confidence levels, and some of them do not have like zero within like 50% confidence, or even like 90% confidence if I increase these contours. So
very good.
That is, sorry.
Yeah. Thank you. Thank you.
Okay, so that was the point I was trying to make. Like some of them don't have zero as a solution. And in these two formation channels, like the dynamical one, you would expect things to be symmetric across.
Okay, thank you. Thanks for clarifying that. Thanks.
Sure. Okay, thanks. Yes, and okay, one more thing to just point out is that like there is also another like observation systematic that things above things which have positive chi-square and high mass can be brighter as they have like power in the LIGO observation band. So this could also be an observation systematic. We would have to like disentangle this by doing some injections where we do one injection in the high chi effective and one injection in the negative chi effective and see whether we can recover both of them. So if we can recover both of them, that means our pipeline was sensitive to both of them, and there is indeed some preference for high masses. But if we don't recover some event here by doing some injection in the data, then it means that this could be observation systematic. So this is what we will try to probe in the next study. Okay, so let me just getting back to this Bayesian evidence point. So there are like some of these events which do seem to show like so this is like base factor preference for having higher modes in the data, and some of these do show higher modes, and some of them do show preference for like higher modes and precession. So you can actually, I think, like divide these new detections into like two categories, I think. So some of these new events we have found, I think, because we included these higher modes in the template bank, we have found some of these new events. But there's a fair population of these events, I think we have just found because we have increased the high mass sensitivity. So this was not just not because we included these higher modes in the pipeline. Okay. Okay, so now let me actually change some gears. I'll talk about another gravitational wave search, but this is targeted towards different objects. So I've just made a pun by having the title as "Searching for Love." So this was actually work done with Hong Sheng, who is a postdoc at the IAS, Tom, who is a postdoc at JHU, Aaron, who is at Texas, and using this IAS pipeline. So when I say love, I just meant objects with large tidal deformability, and the reason for having this title love is given here. So just to back up, like there can be, if you have a tidal field, for example, you can generate a quadrupole moment in an object. And the amount of quadrupole moment that is generated in an object is given by this lambda, which is called the tidal deformability parameter. And this tidal deformability parameter, it scales with compactness of the object. So the compactness I'm saying as the ratio of the radius to the mass of the object. And so you can see that there is a strong power of the compactness. And so when we say like searching for love, what we meant was searching for this love number or this tidal deformability of some of these objects. Okay, and okay, so then going back to some motivation for searching for objects with high like love number or tidal deformability. So earlier in the talk, I mentioned this search pipeline with templates. And you can see that there was like a massive reduction in the data as you go to the right. And this data reduction was dependent on what physics you have in your templates. And so then one worry we had was that you could maybe lose some of these events just because you don't have like some physics missing in the template bank. And currently all match filtering pipelines assume black hole templates, binary black hole templates. Okay, so then let me go back to this formula that I was showing. So the tidal deformability is given by the love number times the compactness of the object to the power 5. So people in the audience are more experts than me in this point. But if you look at like some equations of state of neutron stars, for example, you can see that the tidal deformability, as you decrease the mass of the neutron star, the tidal deformability goes up by a huge factor. So I mean, like and our worry was that like maybe we would lose like some of the events or some of these binaries which have like high tidal deformability, some of these objects. So one parameter region to probe this high tidal deformability is like low mass neutron stars. And another parameter region we were thinking of probing for these high tidal deformability object is some of these exotic objects that people have proposed. So for example, you can have like black holes with scalar clouds. So here you can get significant tidal deformability because of these axion clouds around black holes. So black holes on their own do not have any tidal deformability, but if you have these additional effects, they could have tidal deformability. So you can have some objects which are greater than 1 solar mass, for example, and have a large value of lambda from these exotic theories. Another example for this is you could have like boson stars, which are like these compact stationary configurations of scalar fields which are bound by gravity. Even here you could have like massive objects which have large tidal deformabilities. So our question was whether like there could be some exotic objects with a large lambda, and then we then try to see whether these massive objects with large lambda could be recovered by existing template banks. So here I'm showing like the sensitivity of the existing template banks to these objects in these regions of parameter space. So you can see that on the color is the fractional SNR that is recovered by using binary black hole templates for these binaries. So you can see that when this lambda parameter is like lower than nearly 1000, the binary black hole templates do recover most of the SNR. So you would have found, like if there were objects here, you would have found them using just the binary black hole templates. But if you have objects which have large lambda, you could miss them using your binary black hole templates. So this motivated us to make templates in this region specifically for these kinds of high lambda objects, and then try to do a new search targeting these objects. And I'm running out of time, so let me just like quickly mention that we did not find any significant new events with this new search that we did. So here I'm showing like the expected background. These are the number of candidates with, this is the false alarm rate or the inverse of the false alarm rate. So you expect like this distribution of the false alarm rate just because of this background noise, but and the foreground that we found was not significant enough to claim any detection. So this has been we essentially we found null results in our search, and then we could actually translate these null results into constraints on the merger rates of these kinds of parameters where you have these exotic objects forming binaries and merging. You could constrain that scenario, and this is the range of the parameter space with, this is the upper limit on the rate that you could constrain in this region of parameter space. Okay, so that was my last slide, and then let me just summarize. In the first part of the talk, I showed an effective method, an efficient method for searching for gravitational waves, including these higher modes or higher harmonics, where our search was only 3 times more expensive than only using the quadruple mode. This is in comparison to other searches which have been like 100x more expensive. Then we searched in the O3 data, the observation run 3 data, and found some new mergers, around 10 of them. And in the final part of the talk, I mentioned this new search with high tidal number objects, but we found null results. Okay, thanks.
Okay, yeah, thank you for your very nice talk. And I can already see an hand by Francois Foucault. So can you please unmute yourself?
Yes, thank you for the talk. I was wondering about your last search, actually, the one for the high lambda objects. Could you comment on how you generate templates for those? Do you actually Do you do anything about the merger phase, where maybe those would like disrupt very easily, or is this an extrapolation of the current linear and lambda kind of waveform that we have in the catalogs? Or?
Yeah, so we actually truncate the old waveform close to the merger. So there becomes a point when your stationary phase approximation, which is used for making the templates, that breaks down, and we truncate the waveform at that point. So this was like being model agnostic. We don't know how the merger of these high lambda objects would look like. So let's just be conservative and truncate it at a conservative point. So we were quite conservative.
Truncated before even like a lambda of 1 million object would be tidally disrupted.
Yes.
Okay, thanks.
We try to be as model independent as when we could. So one could do a better search with the more sensitivity if one knows what the merger and the ring down of these high lambda objects would look like.
Yeah, but I don't think anyone has done simulations of the merger of a lambda of 1 million.
Sure. Yes.
Systems. It's probably better to keep it agnostic for now.
Sure.
Are there any more questions for Jay?
I think we have one. Yeah.
Anna, you were saying something?
Yeah, this is George Fuller again. So thanks, Jay, for a great talk. Very exciting. So one thing you mentioned is this issue of using standard sirens to get the Hubble parameter from binary neutron star mergers. And this issue of the degeneracy between distance and, I think, inclination, is that right?
Yes.
And you can beat that down by looking at the higher order modes, which is really interesting. So with GW 170817, if you look at that's touted as a great example of doing this, and it gives a value for the Hubble parameter right between the two values that are supposedly in tension, 67 and 73, but with a big error bar. Yeah. So can you even decrease that error bar for GW 170817?
Okay, so yeah, this is a very good point. So for higher modes, as you can see from even this formula actually. So if you have the mass of the objects, which is like the mass ratio of the objects, which is nearly equal, you don't get like these higher modes which are strong. So in binary neutron stars, when you have objects with similar mass, they don't excite these higher modes. So what you are saying would be very interesting. So if we have in the future, suppose if we have a neutron star black hole merger, which we can find a counterpart to, that will be very interesting, because in neutron star black holes actually there can be these higher modes, and so we would be able to estimate the distance more precisely for this neutron star black hole candidate than we could do for 170817.
Great, thank you, Jay. That clears up a misconception I had. Thanks a lot.
Yes. And another one interesting also fact to mention, also for 170817, I mean, this degeneracy has been a big problem. So people have tried to go around this by claiming that you also see a jet, and you can maybe constrain the inclination of the binary neutron star by looking at the angle that the jet is pointed to. But then this also involves some hydrodynamic simulations. So that has been like that's been another direction which people have tried to take, but with some caveats of using these hydro simulations to determine the inclination. But this is a more cleaner way, I think, if you have these higher modes.
Okay, so I don't see any more hand. So let's thank the speaker again for this very excellent seminar, and we will meet next week. Thank you, Jay.
Thanks for the invitation.
Thank you.